can even prevent them from seeking medical care. So it is very important to avoid stigmatizing people. And we can all do this. How? Basically, by understanding that words matter. Do talk about the new coronavirus, but don't attach locations or ethnicity to the disease. Do talk about people who have or may have COVID-19, people who died after contracting COVID-19, but don't refer to the people with the disease as COVID-19 cases or victims. Do talk about people acquiring or contracting COVID-19, but don't talk about people transmitting COVID-19, infecting others, or spreading the virus, as it implies intentional transmission and assigns blame. Do speak and share accurate information about risk from COVID-19, but don't repeat or share rumors that are not confirmed or language that spreads fear. Do talk positively and emphasize the effectiveness of preventative measures, such as hand washing, but don't emphasize or dwell on the negative or threatening messages. Most importantly, do good. Use your social media account to spread facts and solidarity. This will help us to prevent the spread of COVID-19. Hi, my name is Cassie, and I'm 16 years old. I've seen on social media that the new coronavirus outbreak has provoked a lot of social stigma and discrimination. This is harmful to not only those who suffer from it, but for everyone. Stigma can isolate people. It can drive people to hide their illness to avoid discrimination, and can even prevent them from seeking medical care. So it is very important to avoid stigmatizing people. And we can all do this. How? Basically, by understanding that words matter. Do talk about the new coronavirus, but don't attach locations or ethnicity to the disease. Do talk about people who have or may have COVID-19, people who died after contracting COVID-19, but don't refer to the people with the disease as COVID-19 cases or victims. Do talk about people acquiring or contracting COVID-19, but don't talk about people transmitting COVID-19, infecting others, or spreading the virus, as it implies intentional transmission and assigns blame. Do speak and share accurate information about risk from COVID-19, but don't repeat or share rumors that are not confirmed or language that spreads fear. Do talk positively and emphasize the effectiveness of preventative measures, such as hand washing, but don't emphasize or dwell on the negative or threatening messages. Most importantly, do good. Use your social media account to spread facts and solidarity. This will help us to prevent the spread of COVID-19. Hi, my name is Cassie, and I'm 16 years old. I've seen on social media that the new coronavirus outbreak has provoked a lot of social stigma and discrimination. This is harmful to not only those who suffer from it, but for everyone. Stigma can isolate people. It can drive people to hide their illness to avoid discrimination, and can even prevent them from seeking medical care. So it is very important to avoid stigmatizing people. And we can all do this. How? Basically, by understanding that words matter. Do talk about the new coronavirus, but don't attach locations or ethnicity to the disease. Do talk about people who have or may have COVID-19, people who died after contracting COVID-19, but don't refer to the people with the disease as COVID-19 cases or victims. Do talk about people acquiring or contracting COVID-19, but don't talk about people transmitting COVID-19, infecting others, or spreading the virus, as it implies intentional transmission and assigns blame. Do speak and share accurate information about risk from COVID-19, but don't repeat or share rumors that are not confirmed or language that spreads fear. Do talk positively and emphasize the effectiveness of preventative measures, such as hand washing, but don't emphasize or dwell on the negative or threatening messages. Most importantly, do good. Use your social media account to spread facts and solidarity. This will help us to prevent the spread of COVID-19. Hi, my name is Cassie, and I'm 16 years old. I've seen on social media that the new coronavirus outbreak has provoked a lot of social stigma and discrimination. This is harmful to not only those who suffer from it, but for everyone. Stigma can isolate people. It can drive people to hide their illness to avoid discrimination, and can even prevent them from seeking medical care. So it is very important to avoid stigmatizing people. And we can all do this. How? Basically, by understanding that words matter. Do talk about the new coronavirus, but don't attach locations or ethnicity to the disease. Do talk about people who have or may have COVID-19, people who died after contracting COVID-19, but but don't refer to the people with the disease as COVID-19 cases or victims. Do talk about people acquiring or contracting COVID-19, but don't talk about people transmitting COVID-19, infecting others, or spreading the virus, as it implies intentional transmission and assigns blame. Do speak and share accurate information about risk from COVID-19, but don't repeat or share rumors that are not confirmed or language that spreads fear. Do talk positively and emphasize the effectiveness of preventative measures, such as hand washing, but don't emphasize or dwell on the negative or threatening messages. Most importantly, do good. Use your social media account to spread facts and solidarity. This will help us to prevent the spread of COVID-19. Hi, my name is Cassie, and I'm 16 years old. I've seen on social media that the new coronavirus outbreak has provoked a lot of social stigma and discrimination. This is harmful to not only those who suffer from it, but for everyone. Stigma can isolate people. It can drive people to hide their illness to avoid discrimination, and can even prevent them from seeking medical care. So it is very important to avoid stigmatizing people. And we can all do this. How? Basically, by understanding that words matter. Do talk about the new coronavirus, but don't attach locations or ethnicity to the disease. Do talk about people who have or may have COVID-19, people who died after contracting COVID-19, but don't refer to the people with the disease as COVID-19 cases or victims. Do talk about people acquiring or contracting COVID-19, but don't talk about people transmitting COVID-19, infecting others, or spreading the virus, as it implies intentional transmission and assigns blame. Do speak and share accurate information about risk from COVID-19, but don't repeat or share rumors that are not confirmed or language that spreads fear. Do talk positively and emphasize the effectiveness of preventative measures, such as hand washing, but don't emphasize or dwell on the negative or threatening messages. Most importantly, do good. Use your social media account to spread facts and solidarity. This will help us to prevent the spread of COVID-19. Hi, my name is Cassie, and I'm 16 years old. I've seen on social media that the new coronavirus outbreak has provoked a lot of social stigma and discrimination. This is harmful to not only those who suffer from it, but for everyone. Stigma can isolate people. It can drive people to hide. Hi, my name is Cassie, and I'm 16 years old. I've seen on social media that the new coronavirus outbreak has provoked a lot of social stigma and discrimination. This is harmful to not only those who suffer from it, but for everyone. Stigma can isolate people. It can drive people to hide their illness to avoid discrimination, and can even prevent them from seeking medical care. So it is very important to avoid stigmatizing people. And we can all do this. How? Basically, by understanding that words matter. Do talk about the new coronavirus, but don't attach locations or ethnicity to the disease. Do talk about people who have or may have COVID-19, people who died after contracting COVID-19, but don't refer to the people with the disease as COVID-19 cases or victims. Do talk about people acquiring or contracting COVID-19, but don't talk about people transmitting COVID-19, infecting others, or spreading the virus, as it implies intentional transmission and assigns blame. Do speak and share accurate information about risk from COVID-19, but don't repeat or share rumors that are not confirmed or language that spreads fear. Do talk positively and emphasize the effectiveness of preventative measures, such as hand washing, but don't emphasize or dwell on the negative or threatening messages. Most importantly, do good. Use your social media account to spread facts and solidarity. This will help us to prevent the spread of COVID-19. Hi, my name is Cassie, and I'm 16 years old. I've seen on social media that the new coronavirus outbreak has provoked a lot of social stigma and discrimination. This is harmful to not only those who suffer from it.
Okay, good afternoon to all of you. Today we will be discussing about the pillars and its design related to board and pillar workings. Okay, so in board and pillar workings, there are exactly more or less three types of pillars which you can consider. One is the pillar itself, which is going to be extracted, and then a set of pillars in this Bowden pillar workings are isolated as a panel, and the design of panels require pillars all around the boundary of that panel. So the design of that barrier pillars is another one aspect. Another aspect is the design of the pillar itself, and then the third is the design of the ribs that you are leaving them while depillaring the workings. Okay, so I hope the material for this Bowden pillar workings was uploaded on the MIS. I'll be just discussing the salient features of that lecture material, so that those who have not understood the concepts, they will be able to grasp it. And in between, if you all have any queries, you can type in the chat box. My chat box is on the top, so I'll be able to see it, and then I will respond to it accordingly. Are you all able to hear me? Is the voice quality okay? Can you please type in the chat box? Are you able to hear my voice? Okay, good. So in Bowden pillar workings, okay, so in Bowden pillar workings, the first thing we will discuss is the size of the panels. Now the size of the panel is mostly decided by the rate of the extraction and the period of incubation of the coal. Say for example, if the period of incubation of the coal is 1 year and your extraction rate is X, then what is the amount of coal that can be extracted within 1 year, that much pillar has to be kept in a panel. Okay, and as far as this rate of loading on the panels are concerned, this you can see this graph. This was studied by Salomon, in which he made a graph of the ratio of the induced stress over the pillar divided by the in situ stress over the pillar existing prior to the mining. So if you consider a panel having 3 pillars only, this ratio goes almost around 2.5, but as you increase the number of pillars in the panel, say up to 7, if the number of pillars in the panel are 7 pillars, then this ratio reaches almost to 3, and if it goes to 11 or more, it has reached almost up to 3.5. So this thing was done considering the extraction ratio of 75%. If 75% of the coal is being extracted from a panel, then the magnitude of stress over the pillar, central pillar, will be almost 3.5 times the virgin stress. In another example, the depth to depth to the span ratio was considered. Okay, where h is the depth and r is the span of the pillar, span of the panel. Span is the width of the panel. Okay, so when the ratio of the depth to the width of the panel is 2.0, and when the ratio of the elastic modulus of the overburden divided by the elastic modulus of the pillar, that ratio was when that ratio was plotted through a numerical example, it was found that as this ratio of the overburden to the pillar elasticity modulus increases, this induced load over the pillar increases. So the pillar strength is the integrity of the pillar is dependent upon how much load it is coming on the pillar and also how much the strength of the pillar is there. Okay, so that we will discuss just in few minutes. Okay, so these are the write-up of those two graphs which I have already explained. And then one very good research was done in South Africa regarding the size of the barrier pillar. Okay, and that was done by Rangasamy and others in 2001, where they described the historical evolution of the design of the barrier pillars, which can even be applied for barrier pillars under water bearing roof also. A summary of that is given here. This you need not memorize, but then these are some of the empirical relations which have been used long back in the mining industry, but now this has slowly lost its relevance. Rather, the formula given by Wilson is used frequently. Okay, so these are just for the historical or chronological development of the barrier pillars. What were the in the remarks column it is given that which is not which factor is considered and which factor is not considered, but then these were working, still accidents were taking place in the mines. Okay, so starting from 1846 to 1973, these formulae were quite popular. So this is just for your knowledge and reference sake, not much of relevance as on date. Then in 1983, Wilson gave a formula to evaluate the width of the barrier pillars. This is the formula that is being used to estimate how much should be the width of the formula. So it is given by the sum of two terms into 2, where q is the width of the barrier pillar and c is some exponential decay factor, which how it is calculated that I will show you just now, and xb is the width of the yield zone. So these two, when they are added and multiplied by 2, you get the width of the barrier pillar. Okay, the exponential decay factor is calculated using this formula, that c value of c, when r is more than 0.6 times h. R is the span or the width of the panel. If the width of the panel is more than 0.6 times the depth of the working, then you have to use this formula to calculate the value of c. And in case the span of the panel is less than the 0.6 times the depth of the working, then you have to use this formula. Okay, and here in this formula, h is the depth HP is the height of the working or the height of the pillar which is being extracted, and KT is a triaxial stress factor which is normally taken as 0.3. And then another thing, sigma C is the compressive strength of the coal. Okay, and here this formula is to be used when R is less than 0.63 by H. Now the first term you have calculated for this Q is equal to twice C plus XB is equation 2.1. In this, the first term is calculated using equation 2.2 or 2.3 depending upon the case when the span of the panel is compared with the depth of the working. Now the next term XB is known as the triaxial factor, and this is calculated using this formula. HP is the height of the pillar or the height of the working. Q is the vertical overburden load, or simply gamma H or rho GH. And PS is the support resistance against the face. Sometimes when the pillars are supported with say supports, that time you have to use this PS value using the support resistance formula. But in general, in board and pillar workings, none of the pillars are supported on the sides, so there it is usually considered as a 0 value. And P0 is the allowance of cohesion of the failed coal. So what is the C value of the failed coal? That is given as an input, and this is normally taken as 0.1 MPa. Okay, and KT has already been discussed here, triaxial stress factor. Okay, so using this formula you can substitute this value XB into formula number 2.1, and with this the value of the width of the barrier pillar can be calculated. So far this calculation of the width of the barrier pillar is concerned, people have not talked about the factor of safety of these barrier pillars. Rather, they have just tried to estimate what is the width of the barrier pillar. Okay, now coming to the design of pillars. Like design of any structure, the design of coal pillars in board and pillar working mines essentially consists in knowing precisely the two things. One is the strength of the coal pillar and another is the load on the pillar. And when you link these two things with a desirable these two things, you get a factor of safety. Now how do we calculate the factor of safety? Say for example, 1 minute, I will take the pen. Okay, before we write something, just let us consider that this is one sample. Okay, now I am trying to compress it. So the load at which it breaks is the strength of the material, and if you give more load it will crush faster. So in that case the factor of safety will be less than 1. Now if I give less load, still this sample is taking load but it is not breaking, so the factor of safety will be higher than 1. So factor of safety will be calculated as FOS is equal to strength by stress. Okay, so this way the factor of safety is calculated. So when you link the strength of the coal pillar with the load that is coming, load is the stress over the pillar, then you get the factor of safety. Now it is not only the material strength of the okay, are you seeing the PDF? Rather, it is not only the strength of the material, rather the other factors also play a vital role in the determination of factors that are affecting the strength of a pillar. Okay, the most significant one is the depth of the working from the surface, height of the working, thickness of the seam, how the seam is dipping, the dip of the seam also plays an important role, and the width of the galleries, strength of the coal, of course it is there, and strength of roof and floor rocks. Say for example, if the roof rock is very weak and the pillar is strong, the pillar will go on punching into the roof, or else if the floor is also very weak, the pillar will punch into the floor. So these factors also play a good role in affecting the pillar strength. Presence of water, weathering, partial extraction methods, or the full extraction method of the panel. Okay, all these factors, they play a role. So when we talked about the factor of safety of the pillars, the first thing comes into our mind is how do we estimate how much load is coming onto a pillar. Okay, so this is the formula for calculating the load that is coming on a pillar. It is gamma h or rho gh multiplied by width of the solid pillar plus B is the width of the gallery divided by WP is the width of the solid pillar whole square. This is calculated using tributary area method. Okay, that I just give you a brief of that. Suppose this is my pillar and its width is W, and all around this I have galleries. And the width of the gallery is, say for example, it is B. Okay, now this around this pillar there will be a center line. Okay, that means up to half the width of the gallery, the load of the overburden will be acting. Okay, if you see in section, it will look something like this. Okay, I'm sorry, the figures I'm not able to draw correct because of the constraints in writing tab. Somehow I am using my writing touch screen of the Dell laptop and trying to teach you, but this will make this, I hope this will make you understand the concepts. Now say for example, this pillar, the shaded one is the pillar and this white one is the gallery, and this side also, that is coal. So this is gallery and this is another gallery. Okay, so if the pillar is extending on both the sides, this complete weight of the overburden is acting on this pillar. And what is the width of this pillar? Width of the pillar is W, and the gallery width is here is B by 2, and this side also it is B by 2. Okay, that means the width of the column is W plus B. That is the width of the column in this side, and in the opposite side, again, since this we are considering a square pillar, so the total area of the thing will be W plus B by 2 whole square. Okay, and gamma into H, gamma into H will be the load that will be acting upon the pillar. Okay, so this is stress divided by area, so it becomes the load acting on the pillar. Now this total load is shared by only the width of the pillar, this one, and the area of the pillar here will be W square. So this gives me sigma V, or we can say the load that is acting on the pillar will be this value. Okay, so this is how you calculate the load acting on the regular array of pillars. Okay, I am not seeing any chat. That means you are understanding the concepts. In case if you have any issues, you just type in the chat. I will revert back to it. Okay, good. So this is how the load that is acting on a pillar is considered. Okay, so for rectangular pillars, in a similar way you can derive it for rectangular pillars also. In that case you will have WP and LP. Okay, so this is nothing but the area of the complete column of the coal that is going to act over the pillar, and this WP into LP will be the solid area of the pillar. This is how the load coming on the pillars are calculated. Okay, now this theory is known as the tributary area theory, TAT. In short, people call it TAT, tributary area theory. And this theory is applicable only for pillars which are under regular array. That means for a development workings, you can very well estimate the load on the pillars using a tributary area method. But the moment Okay, Sampada has asked that the depth of working is measured from the surface to the top of the pillar or to the bottom of the pillar. Good question. See, in the figure, I will show you the figure. Here rho GH, this rho GH, are you able to see the pictures? Okay, let me switch to the scribble. Okay, so this depth of the height of the column will be up to the pillar, because this is the column of the rock that is applying load onto the pillar. So obviously this H has to be up to the roof of the pillar. Okay, so let me move forward. We are in page 2 only, and it is now 4:20 or 30. So okay, so when your pillars are inclined, then in that case the horizontal component of the stress will also act, and if K is the ratio of the horizontal stress to the vertical stress, and if your seam is inclined at an angle alpha s, this load acting on the pillar can be calculated with this formula 2.7. Okay, this can be proved. It's an extension of the tributary area theory, but now I am not considering. Those who are interested can ask me separately. Okay, so this figure was here. Okay, so this is how the tributary area theory is applied. Okay, so this black one is the coal and this white ones are the galleries, and this column of overburden will be giving load onto this pillar. So area of the column is more, area of the pillar is less. This is WP. So obviously the stress acting on the pillar will always be more than the stress, more than the in situ mining stress. Okay, so this big shaded one is WP plus B, that will be the area, and this WP square will be another area, and then accordingly you find the stresses. Now another problem with this tributary area theory is that here also we are making some sort of approximation, whereas if the rock is elastic, the load on the pillar will not be uniform. It will be higher at the corners and then it goes down, and then again when it reaches towards the other corner it slowly increases and becomes highest. So in fact it will make a shape of inverted umbrella. This load will become an inverted umbrella. How this can be done is this is estimated is, you can see we had studied in the Kidd's equation. Okay, so if this is my tunnel, so what will be the value of sigma p, normal stress or the tangential stress acting across this? It will be sigma theta will be highest. So if you start plotting sigma theta, it goes on reducing and it reduces to certain extent. Suppose we have another tunnel here, so the stress will reduce here. So see, if you have two tunnels or two excavations, the stress distribution, this becomes the distance, the area between these two tunnels acts like a pillar, and because the induced stress is reducing, it takes the shape of an umbrella. Now from the other side, if the two tunnels are made into a square thing, so it becomes an inverted umbrella kind of thing. Okay, so this is how the stresses will behave over the pillar, but this reduction is very less. So generally people consider that this stress is uniform over the pillar. Now in case if the pillar starts behaving like a non-elastic material, or if there is a consideration of the plasticity, then in that case this reduces further as shown in the dotted line. Okay, now some people have tried to use alternate methods different from the tributary area method, and they use numerical modeling. Okay, and Roberts in 2002 he conducted a numerical analysis by varying the percentage of Young's modulus elasticity, and this is the ratio which he said that let RL be the ratio of the model stress over the pillar and the load calculated over the pillar by the tributary area. If you divide this, he said that let us consider this as RL. Okay, and he considered the elastic modulus of coal as 4 GPa. Okay, so if the value of RL is less than 1, this indicates that the model layout is always less than the load calculated by the tributary area. And he tried to plot a graph of this RL can also be taken as a percentage deviation from the tributary area load. Okay, so he calculated this RL versus panel width to depth ratio, and he found that this value is less than 1, that is less than 100%. That means RL value is less than 1. This indicates that the modeled load is always less than the tributary area theory. That means the load coming on the pillar is less than what we calculate using the tributary area theory. But then width to depth ratio, if it is very less, it goes up to 94%. That means you have an error of only 6%. So the tributary area method of calculating the load on a pillar varies by only 6%. So it can be said that you can safely use this tributary area method for calculation of the pillar load on a conservative side. Okay, that means the tributary area is giving more load. So at a higher load, the factor of safety reduces. That means you need to model the pillar having lesser safety, showing lesser safety, but in actual it will have a higher factor of safety. So this way you are on a conservative side. Then he carried out some parametric analysis on how the loads, this is again RL value, that is the load of tributary area versus the percentage of extraction. So if the percentage of extraction increases, the modeled load goes down very fast. So here, if you, this left graph is for the regular pillars, but when you start extracting, the tributary area will give you almost up to 40% of error if you have an extraction ratio of 85%. In fact, 85% of extraction of coal is more or less impossible in Indian scenario. Still, if we consider that 60% coal is taken out, so you get 10% of error, and up to 20% of error you can get when the extraction ratio is almost 85%. So this graph clearly shows that the tributary area theory cannot be applied to irregular pillars or when okay, some questions are there. Subham Sim has asked, but in real life pillars behave elastically or non-elastically? Okay, that's a good question. See, rocks, we had studied in the properties of the rock earlier in the lectures. The lecture on, if you remember, the complete stress strain curve of the rock. In that, what we studied, that if you load the sample at a lower load, then it behaves elastically. Then if you go on increasing the load, then it shows a non-linear tendency. Okay, so there also it is non-linear, but it is behaving elastically. But as you load it more and more, it fails, and in the failure region it acts plasticity is considered in the failure region. Okay, so now this concept I must clear it to you. See, we go to again the scribble board. Okay, you try to correlate with the Kirsch equation. Okay, are you able to see this? Let me check. Okay, you are able to. You must be able to see this scribble box. Okay, so in the Kirsch solution of Kirsch equation, what we had studied, that this side, on the sides of the tunnel, the rock element is loaded uniaxially, isn't it? And as you go deeper into the rock, the element inside the deeper zone will be loaded triaxially. So obviously when the rock is loaded uniaxially, its strength is less. So at the corners, so if these are two tunnels driven here, and the other, so the material in between them is acting as a pillar. So whatever material is near to the skin of the pillar, that will act plastically. Okay, another example. Sir, what is RL? Please explain again. Okay. See, this RL concept is to find alternate methods for estimating the pillar load. One method is the tributary area method. Okay. Another method could be you can use numerical modeling to find the load acting on the pillar. Now you measured the load acting on the pillar using numerical modeling, and then you calculate with hand the load that is coming on the pillar using tributary area method. Okay, both are load, but you need to compare whether the modeled value is more or less with respect to the pillar load using the tributary area method. So in order to find the find the ratio of these two things, you need to compare. So you usually take the ratio of two values and say that there is this much percentage of deviation. So this is RL is nothing but it is basically the percentage deviation with respect to the tributary area theory. And this RL, the scientist Roberts, he tried to plot it with respect to the width to depth ratio of the pillars, and then he found that even the width to depth ratio goes 4.5 or so, the load is not changing much. It is changing by only 6%. One is 100%, that means modeled load is also same as the tributary area load, and 94 it shows that the modeled stress is 6% less than the value calculated by the tributary area method. I hope this has cleared the doubt. Sir, why would the rock behave plastically near the okay, good. I have to refresh your knowledge of Kirsch equation again. This is all application of the Kirsch equation here. Okay. See, coal is a weak material, and if the depth of working is very high, say for example 300 meters, so at 300 meters what will be the vertical load? 2.7 into 3. How much is 2.7 into 3? 27 दूना 54 और 27. How much? I have to calculate it. Okay, 2.7 into 3. Almost 8.1 MPa. Okay, so that will be the vertical load. That will be the sigma y value here. Okay, 1 minute. Okay, sorry, you are not able to see the scribble pad. I'll show you the scribble pad first. Okay, you are seeing the scribble pad. Okay, so sigma y is equal to 8.1 1 MPa. Okay, 300 meter depth, 2.7 I have taken. Okay, it is 8.1 MPa, and say this horizontal stress will be almost 1.5. Okay, 1.5 to 2. So let us say that it is up to 12 MPa. Okay, and if the compressive strength of the coal is 3 MPa, what will be the value of sigma theta, that is at sigma theta at the skin of the pillar? That can be calculated using Kirch's equation, right? And if the induced stress at the skin of the pillar is more than the strength of this coal, the coal is going to fail. Okay, this calculation we have to just check okay, whether it will fail or not. That has to be calculated. But say for example, if the induced stress has become more than 3 MPa at this skin, so it is going to fail. The moment it fails, it goes into the plastic region. Try to correlate it with the complete stress strength curve of the rock, okay, which we have studied earlier. So at the skin of the pillar, the rock is in plastic state, whereas here when it is loaded triaxially at this point, the strength of the coal is more than the strength here, that you have studied in your lab using the triaxial strength formula. Okay, so here the chances of failure is less. So at this point the rock is loaded much below its breaking strength. So here it behaves elastically or non-linearly. It depends how much stress is coming on this. Okay, is it clear? Hope this Deepak would have understood this. Okay, then Paulussen, he tried to give the load transfer distance formula. Okay, that is not much used. In fact, he you can just read it for your academic interest. Okay, but later at the end he also said that this method must be applied for estimating the overall pile stability rather than designing the pillars. So this LTD method is not used, but mostly people use only two things. One is the tributary area method, and another is the numerically modeling method. And in numerical modeling method also, these two graphs, this is showing that for regular pillars it is only 6% of difference, but when you go for board and pillar workings, when you start extracting the pillars, the array of the pillars is not regular in that case, and once the array is different, the tributary area method can give you error up to 60%. So there you really need to know the load on the pillar using numerical modeling. Okay, so this Paulussen is just for your academic interest. Now another interesting thing of again academic interest, that is the history of the development of the coal pillars. Okay, and in that 4 or 5 pillar formulae, those are important, which I will tell you subsequently in this lecture itself, which are the important ones for calculating the strength of pillars. So now again coming back, now I would like to correlate the things with you again. So we are considered with the factor of safety. Okay, the factor of safety is linked with the load coming on the pillar and what is the strength, and the factor of safety is correlated here with the strength versus stress. So up till now we have discussed how to estimate the stress of the pillar. Now we will be discussing how to estimate the strength of the pillar. Once you know the strength of the pillar and the load acting on the pillar, you can very well calculate what is the factor of safety of the pillar. Okay, so we switch to now finding the strength of the pillar. Okay, see, this science of pillar design, according to Coulomb, is traced back to 1773, in which Christopher Mark is another known name in the area of rock mechanics from NIOSH, USA. Okay, he is a rock mechanics scientist in the National Institute of Occupational Health and Safety, which comes under CDC, that is the Center for Disease Control in USA. Okay, so he traced back the history and he said that in 1773 itself, people were thinking about the scientific design of pillars. But the first documented thing came in 1911 by Bunting. Bunting, what he did, he tried to test the strength of the different sizes of cubes and prisms, and he tabulated them in a table in the order of increasing order of size, and he found that there is some correlation between this. So this is what prompted him that if we increase the size of the sample, the strength increases. Okay, then one important formula was by John Edward Nathan. Okay, this is he has written a book in 1928, that is the Coal Miner's Pocket Book, and he gave the formula for the strength of pillars as Cp is the strength of pillar, C1 is the coal strength, normally which varies from 4.8 to 7 MPa, and if Wp is the width of the pillar and Hp is the height of the pillar. So here onwards you just note down, if you have notes, that we will use the symbol Wp as the width of the pillar and Hp as the height of the pillar and Cp as the strength of the pillar. Okay, so this formula was given by him. Later on, Greenwald, he carried out tests on samples of 30 meter size. You see, all this, what you observe is that width to height ratio, these are all power functions here. Okay, and the general formula, whatever has been developed, more or less you will find it in the form of like this. Where is the scribble? Okay, Cp is equal to K times W power alpha height power beta. Okay, this is known as the power formula, and almost for 100 years people had been doing research on finding the different kind of formulae for estimating the strength of the pillar. Now, why this formula has been, this research has been going on for hundreds of years on finding the power formula is because in every region of the globe the coal pillar behaves differently, geology behaves differently. So for their own country they develop their own formulae. Okay, so this was by Greenwald. Another was by Holland and Gady. He used the dimensions of the specimen and the strength of the coal specimen. Here he used 1 inch cube of the sample in the laboratory. He tested it and he called it sigma C25. Okay, and SC is the coal strength specimen. He tried a specimen of the regular thing which you use by the laboratory methods. Okay, so he found out that for a 1 cubic inch of size this will be the strength, and this sigma C25 is used because 2.5 centimeter is 1 inch cube, so sigma C25 has been used here as a notation. Okay, and then he used to find the pillar formula WP by HP and so on, so this was given by Holland and Gady in 1957. He again is in 64 modified the exponent to a different value. Now in coal mines regulation in 1957 the size of the pillars were defined this way. If your depth of working is 60 meters and the gallery width is not more than 3 meter, then you have to maintain at least 12 meters of pillar. Now here in coal mine regulation, I would like to just mention you that in coal mines regulation when they say the pillar to be center to center, this means suppose I have two pillars, from this center to this center, this is the width of the pillar. Or in another way you can say that if this is the board width, then W plus B what happened? W plus B will be the width of the pillar center to center. Okay, whereas W is the solid width of the pillar. Okay, so this concept, this is just geometry of the pillar. Okay, coming to the PDF. Okay, you have not seen okay, see, I'll tell it again. I think you might not have seen the scribble pad. If we have two pillars, the distance between the centers of the pillar is treated as center to center, or else in another way you can calculate the center to center distance of the pillar using the gallery width. If gallery width is B and solid width is W, then the center to center distance is taken as W plus B. This you can draw the geometry and you can verify it yourself. Okay, not a big deal. Okay, so we come to PDF again. Okay, so depending upon what is the width of the gallery, 3 meter, 3.6 meter, 4.2 meter or 4.8 meters, and for various depths, this has been specified by the DGMS that this should be the minimum size of the pillars, that is distance between the centers of adjacent pillars. Okay, you can go for a higher size of pillar, but you cannot go for a lower size of pillar. So this was given in 1957 in CMR, and still it is being worked out, because this gives a very conservative side of the comes on the conservative side of the pillar design, and it's very safe, over safe, we can say that it is over safe. So that has been used. Now one big thing came through Salomon and Munro in 1967. This is a very important formula as far as your academic things are considered, or the practical aspects are considered. Many people are using this formula throughout the world, because this was statistically developed through analysis of 96 intact and 27 collapsed pillar geometries of South African coal mines. Such a huge database of practical relevance that was gone into the derivation of this formula. And still, if you don't have any formula for the what you can say, the strength of the pillar or any other thing, you can use this formula safely. People use many formula, but they also start comparing with Salomon Munro formula also, and verify that whether their formula is somewhere near to the Salomon Munro formula. Okay, so this width to height thing was used. KSM is one constant. This constant is taken as 7176 kilopascal. So this is an important one. Now in India, the same thing was modified by CMRI by Chevre in 1987, and he gave the strength of the pillar as this. Okay. Okay, later on Obert and Duval gave another formula considering the width to height ratio and another constant C10. Okay, Cook gave another formula. Wagner gave a concept saying that the central portion of the pillar has higher strength and the outer pillar has lower strength. This is nothing but again the extension of the Kirch's equation concept, which we discussed now, that the skin of the pillar will have lower strength, and as you go deeper into the pillar, its strength will be higher. Okay, so this concept was basically given by Wagner in 1980, not by correlating with the Kirch's equation, but through his own methods of study. Okay, so this thing can be correlated with the Kirch's equation also. Binaveski in 1975 he gave another formula that's not so important. Okay, Hustelid again tried to find the sizes and tried to give the formula, not so important. Parasiu, he tried to give the shear component and normal component over the pillar for inclined pillars considering the K value. Okay, this formula you can read through the books of William G. Parasiu, available on the net also. Okay, now using numerical modeling, the strength was calculated by Agapito and Hardy. Again, not so important, but you must know it, you can read through it. Now in India, thus extended the concept of Wagner again. And what he did, he used rock specimens of different length to height of 54 millimeter dia samples, and he loaded them onto a loading machine. Okay, so the dia was constant, only the length was varying. So width to height ratio will automatically vary. So this graph is the classic graph given by Das, which indicates that as the width to height ratio is less, it simply behaves like a sample in the laboratory. The pillar will behave like a laboratory material, but as it increases, you see here it has shown a failure, and then it goes down, and if you go on loading it again and again, still it has a load bearing capacity, and then here this again starts picking up. The strength starts picking up because of the triaxial confinement. Okay, so this portion of the graph, which is increasing after the failure, is known as the strain hardening concept. Okay, so he gave the concept of strain hardening, which, so according to this formula, say for example, if the width to height ratio is 9.0, that means the pillar will take some load, it will fail, and still it will have a capacity to take the load even after failure also. And if the width to height ratio is more than 13.5, then it goes on taking the load and it doesn't break. So with this research, he said that pillars having width to height ratio on a higher side, which is known as squat pillars. Squat pillars are those pillars which have width to height ratio more than 5. So that those kind of pillars are non-destructible. You cannot destruct those pillars. That will stay for a longer period of time, and it will never fall. Mark Binaveski, they gave this formula, and this formula is being used by one software from NIOSH again, which is known as ARMPS software. ARMPS is analysis of retreat mining pillar safety. Okay, so that software uses this formula for calculating the stability factor of, it is not safety. ARMPS is analysis of retreat mining pillar stability. Okay, so here they use this formula to find out the stability factor. They are not calculating the FOS. They have come out with a method for calculating the stability factor, which is more or less synonymous to the factor of safety. Now, so far every people have discussed about the length, the size of the pillar, width to height ratio, but nobody talked about what will happen to the squat pillars. Okay, so when the size of the pillar is more than the width to height ratio is more than 5, that is taken as squat pillar. So for squat pillar, Madden gave a formula in which we considered one thing, that is R0 value, which is known as the critical width to height ratio, which is taken as 5, and that thing was included. So when you need to calculate the strength of the pillar for squat pillars having width to height ratio more than this formula gives a better estimate of the strength. Now, so this is another important thing. The first one is the Salomon-Monro formula, second one is the ARMS formula, and third is this one by the South African, that is Madden's equations for squat pillars. And then in India this equation is of more relevance. See, all people, they discussed about weight to height ratio, but nobody tried to consider the depth of the working or the in situ stress. So Sevre in India, he developed an equation which takes into consideration the depth of the working also, including the width to height ratio, and the laboratory strength of sigma C25 is the laboratory strength of the 1 cubic meter, 1 cubic inch of a sample. Okay, so this has been in use in Indian context for design of pillars. And when you go for design of the stooks or reefs in the Bowden pillar working, then this formula is used for finding out the strength of the the ribs strength can be calculated using this equation. And as far as factor of safety is concerned, if anything has a factor of safety less than 0.6, it is going to fail immediately. And if the factor of safety lies between 0.6 to 1, it is stable for a few days. And if it is between 1 and 2, it is a short-term stability which can fail in slowly it will fail progressively, and it can fail in few years. And if you want to design any structure which has a long-term stability, then you need to have a factor of safety 2.0. So inside a panel, a rib if you have to extract remotely using machines, so here it is dangerous, but still if your machine is able to extract the things faster, you can go for the rib stability up to lying between 1.0 to 0.6. And for panels or the stooks, if you want to keep it stable for a few years, then you can use it for as a factor of safety 1 to 2. Okay, these are some of the values of the in situ strength of the coal which can be of academic interest. Now, when Das gave the concept of the squat pillars, that they are indestructible, in US, Maleki in 1992, he reported failure of 7 US coal seams. Till now, people were believing that the pillars are indestructible when they are squat. That concept was refuted by Maleki, and he gave the formula for the squat pillars strength. Okay. Now, a geologist in Gale in 1999, he tried to correlate the geological contents and strength versus width to height ratio, and he tried to carry out lot of statistical analysis from the given data, and he came out with a confinement concept. And he said that if you have weak silt stones, the operating range of factor of safety should be in this area, and so on. So for different geological conditions, he gave this classical graph. Now people have used numerical methods using FLAG 3D, okay, to find out the strength of pillars. This was done by Sevre in 2006. Okay, so still research is going on, design of the strength of pillar, but despite the facts that textbooks have considered laboratory testing as integral part of the pillar design for nearly 30 years, it has remained controversial. One reason is that coal is notoriously difficult to test. It is very difficult to test coal in the laboratory. Even 6 to 7 times testing is required and you don't get a real estimate of the strength of the coal. So lot of research has to be done in this area. Okay, so this is about the pillar design approach. Now I would like to tell you that so far we have done only 2 assignments. One assignment is left out. So this is the questions for the assignment that you need to solve. The question is that a 2.5 meter thick horizontal ore body is located at a depth of 100 meter with the rock having a unit weight of 25 kilonewton per cubic meter. Sir, have you mentioned RL numerical modeling not for design but required only for cross-check, TAT method, etc. Correct. James is asking, sir, have you mentioned RL numerical modeling not for design but required only for cross-check, TAT method? No. See, this RL concept was used just to show that what is the difference between the calculation of the tributary area load versus numerical modeling load in case 1 is when the pillar arrays are regular. So in that case they found that it is only 5 to 6% of error. But in second case, when the regular pillar array of pillars will not be there, that is when you have started mining, so the array of the pillars are disturbed. Okay, so in that disturbed case, the load on the pillars will vary up to 40%, 40 to 60%. Okay, so in that case you cannot use tributary area method. So tributary area method is just applicable for finding the stability of finding the load on the pillars when they are a regular array. But the moment you have an irregular array, there is no question of using tributary area theory. You need to go for finding alternate methods for finding the load on the pillars, and one of the methods is the numerical modeling method. That is what he tried to justify using these 2 graphs. Hope it is clear now. Okay, so we come back to the numerical question. Okay, so here the initial mining layout is based on 6 meter room spans and 5 meters of square pillars. So here the B value, the board value or the width of the gallery is 6 meters, and the width of the pillar, the solid width of the pillar is 5 meter. Okay, and the strength of the pillar is determined empirically by the formula. When you see this formula, this is nothing but Salomon-Munro formula. Okay, so I hope number 1, that is the determination of factor of safety of initial mining layout, will be an easy task for you. Will you be able to calculate it? What you have to do is, you have to find out the load on the pillar using tributary area method, and use the height and width of the working. Height of the working is 2.5 meter, okay, and width of the pillar is 5 meter. So you can very well calculate the strength of the pillar. So strength divided by the stress will give you the factor of safety of the initial mining layout. Now here comes a catch. This assignment I am giving you because when you solve this question, you will get an insight into how people design the workings of board and pillar. Okay, so there could, now when you do this calculations in number 1, I have solved it. You will get the factor of safety as 0.67. Okay, in question number 1, the answer will be 0.679 will be the factor of safety. This means that the layout is unstable. Now when the layout is unstable, you can have 3 strategies. One strategy is you reduce the 6 meter room span. Okay, so when this reduces, the strength of the pillar increases. Okay, let the width of the pillar be 5 meter, but reduce the gallery width. Okay, so in that case, the factor of safety will start shooting up. So when you reduce the room span, it is shooting up. So what should be the room span at which this factor of safety of 1.6 can be maintained? If you want to maintain a factor of safety of 1.6, then what should be the width of the gallery or the room, so that you get a factor of safety of 1.6. Another thing could be, let the span be 6 meter, width of the gallery let it be 6 meter. Somebody will say that no, my machine will not work in less than 6 meter of gallery, I need 6 meter gallery. Then what you have to do? The next strategy is that, okay, let us go and increase the width of the pillar, because as you go on increasing the width of the pillar, keeping the height constant, the factor of safety increases. Okay, so for maintaining 1.6 meter of 1.6 factor of safety, you need to increase the pillar width. Okay, so I just give you the answer for 2 ka A part will give you a width of this room, or the board width or the gallery width, to 2.16 meters. Okay, and for strategy 2, here is a catch. See, width you are varying. Okay, so the strength formula will contain W, but height is taken as 2.5, and then you calculate the tributary area load keeping W as a variable. Okay, so when you use the formula of FOS is equal to strength by stress, then 1.6 is equal to factor of safety. Strength will consider a variable W, and the load will also consider a value W, and then you have to solve this equation in as a function of W, and that can be solved using Newton-Raphson method. And then for B, you will get 3 iterations, and you will find that the pillar width turns out to 9.2 meters. Okay, and strategy C is, some people will say that okay, I will not reduce the room span, I will not reduce the pillar size, I will keep them fixed. So the next strategy is to reduce the height of the working. Okay, so when you reduce the height of the working, automatically the factor of safety increases, and here in that case the height of working turns out to be 0.68 meters. The answer is 0.68 meters. Okay, so these things you need to calculate that way. And then the third question is, which of the options A, B and C above are more suitable for mining, and why? See, one concept of the recovery I did not mention, so I will just brief you about. Okay, Sampada is asking any method that we can use other than Newton-Raphson method. See, you get a equation, finally you will be getting a equation something like 0.98 into W power 2.46 minus x square minus 12x minus 36. Okay, you can use your calculator. Okay, and if you have left your calculators in the hostel, probably that will be a very tough thing for you. But one thing I can suggest is that there are a lot of I don't think that a big calculator will be required. A lot of apps are available in the mobile with which you can calculate it. Okay, and you consult the Newton-Raphson method on the net. If you have left your notes, you will be able to do it. I will give you sufficient time to do this assignment. Okay, and finally when you all submit this assignment, I will be uploading the answer of this also. So for the last thing, the number 3, which of the options A, B, C are mentioned above are more suitable for mining, and why? See, when you have to go for mining, what is the best option which is giving me maximum recovery of the ore? If I am able to maintain a factor of 1.6 using these 3 methods A, B or C, which of them is giving me maximum recovery? That will be the best suitable option for me, right? So the formula for calculating the concept of calculating the recovery, I will just show you the concept. I have to use the scribble board. Okay, I'll use this figure itself. It will become dirty if I use this figure, but anyway, let me try. Okay, I will not write much. See here how to calculate the recovery. See, in a regular array, W plus B, that is the central line area. Let me use the PDF. No, okay, let it be this one only. Okay, so W plus B is the total area that is available for me for this pillar. As far as the if I distribute the complete array, so for one pillar the area that will be considered by the pillar is W plus B. Okay, so W plus B is the area available for me, which is having mineral. Okay, W plus B whole square, if we consider another dimension. Now in this, if I extract completely W, then W square has been taken. Okay, and this is what percent of the total available area? W plus B by 2, W plus B whole square. Okay, so this is equal to, this value is equal to 1 minus W by W plus B whole square, and this is termed as the percentage recovery. Okay, so in each case you have to calculate the recovery, and when you are calculating all these values, simultaneously you calculate it for the what you say is the recovery for each case, and finally you will be commenting that whichever is having the maximum recovery, that is the best solution. So this is just the solution strategy I have given you. Still, I think most of you will be finding it difficult because online method I am not able to see your faces, and I am unable to get any feedback on whether how the students are understanding or not. Probably this might have gone one way, but still I give you a hint. This problem has been defined from a concept Ashir Khan. I will come to your point just after discussing this problem. I'll resolve your queries. Okay. So see, this problem has been designed from a case that is already available in the book of Brady and Brown. Okay, so I hope all of you must be having that book with you. If not, you can get it downloaded, and then you can use it. Read that chapter on pillar design. At one place this complete concept has been discussed, and then you try to solve it. This will really give you a good insight into how we design a pillar in board and pillar workings. Okay, and this assignment I will post it in the Google class. I request all of you to please join the Google class, and request all of you to write it on a paper. Take a scan using Google Drive scanner or Cam2 scanner, and then upload it in the Google class itself, so that I can evaluate that third assignment. So we are left with only one assignment. Do it. But the problem with Google assignment is that it will become very difficult for me who has copied and who has not copied. If I'm able to match the handwritings, then only I can take a action. If I'm unable to match the handwriting of two people, it becomes very difficult for me to say that whether it is an original assignment submitted by the student or he has copied it. Okay, so that is another disadvantage of this technology. Okay, but anyway, I will request you all to solve it yourself. Take help through discussion and WhatsApp, and try as much as possible to solve yourself so that you get a good insight into the problem solving approach for this. This is one very good practical example of board and pillar design, which is going to solve your going to give you a good insight into the pillar designing aspect. And see, this here we have used the formula of this Salomon-Munro formula. If suppose you have to design it for a metal mine, a room and pillar mining, and there you want to use the Severus formula, then the complete thing will change. So according to the pillar strength formula, the calculations will also change. So if you have time, you can try it yourself, get satisfied. Okay, so that's all about this. And Asir Khan's query is, what is the threshold value of FOS for stable or unstable? Okay, Asir, I had discussed this FOS for stable or unstable. See, you have not asked whether it is pillar or any other structure, but still I will show you that PDF. See, this is the table that can be used for your design of structures. Suppose in a rib, if your factor of safety has gone less than 0.6, within hours it is expected to have a failure. Okay, you have asked it for filler. Now let me generalize it for everybody. Okay, so any structure which you are going to design in an underground, if you want to go for design of any civil structure, you need to have a factor of safety more than 2.0. Okay, some people use 1.25, 1.5 also. This is a debatable concept, but in general, this table is based on the Severus failure criteria, and the designer, they resort to design with a factor of safety more than 2.0 if they are going for long-term stability. Okay, suppose in a mine roadway, the haulage roadway, okay, that has to serve throughout the life of the mine, and there you cannot play with the factor of safety. You have to be on a conservative side. So in that case, you always go for a higher factor of safety of 2.0. That is more than enough. And say for within a few years, if you have to if you think that if that structure is not required underground, and within few years it hardly bothers me, then say for example your temporary roadways in the mine, okay, near to the what you said, this panels, okay, or if you have some stokes which you just want to take out and then go out, then there you can go for a design which has a factor of safety less than 1 to 2. And this 0.6 to 1 is normally used when you are extracting the ribs in board and pillar workings. Okay, so when you are taking out a slice in the depillering and you are leaving a rib, so the width of the rib is an important thing. How much width you can take? Normally it is mandated that you have to leave a 3 meter width of rib. So when you are leaving a 3 meter of rib, use the Severage formula, this formula, this S equation 2.40 to estimate the strength of the rib. Okay, and the load you have to, in this case, estimate through the numerical modeling, because when you are doing depillering you cannot use tributary area theory. So with that you find out the factor of safety, and if it is lying between 0.6 and 1, you can very well extract it. Okay, and then it is again said that once you go to the end of the slice, and when you start retreating, you start taking away the mineral from that rib also. That is known as robbing in the coal stoke, robbing of the ribs. So when you have to go for robbing of the ribs, again you need to calculate up to how much thickness I can rob the this rib. So in any thickness which is giving you a factor of safety less than 0.6, you need to be very careful. It can fail immediately or within few hours, and all your machine and men will be entrapped into this. So that care has to be taken. Okay, but in practical situations, the guidelines which have been given by DGMS, they are very conservative and they work very well. You need to calculate all these things when you are really thinking of improving the recovery or the efficiency. Then you really need to go for these calculations. Okay, I hope this has cleared your doubt. So can we consider value of 1.0 for pillar? See, pillars, for pillars, if a pillar has to be extracted using splitting and slicing, okay, so it takes time for splitting and extracting, and it cannot be done in a few days. At least for one pillar you require more than a week. So there you cannot go for a factor of safety of 1.0 for the pillar. Okay, this Deepak Prabhakar, book name you mentioned. The book is by Brady and Brown. I will just show you the color of the book. Let me check if it is here or not. Oh, it is not with me. Rock Mechanics for Underground Mining by Brady and Brown. Okay, this Deepak Prabhakar. So that assignment problem you can get lot of hints, or in fact you will get the same data there. It has not been dealt in detail, but based on today's lecture and the reading you will be able to solve it. I'm fully hopeful. Okay, or you can do one thing, you try to solve it yourself and then try to compare with the book, so that you really come to know where is the mistake you have made. Salini Mukherjee, sir, depending upon which factor that formula given in the question S is determined. Depending upon which factor that formula given in the question S is determined. See, the strength S, I think this S, just a minute, which S you are talking in the problem? Okay, S, right. So in the problem, this S is basically the strength of the pillar that has been mentioned. I'll show you the problem here. Okay, this S is the strength of the pillar. Okay, and this strength is given by this formula. That means the user is using the Salomon-Munro formula for estimating the strength of the formula. Okay, this formula can be used, say for you want to do it in Indian condition, then instead of S you can choose the Severance formula, but then that will be a big thing, lengthy thing, and difficult for you to calculate for the first time. Once you solve this problem using this Salomon-Munro formula, calculating the thing using Severance formula will be easier for you, and that will give you a more insight into the problem solving approach. Okay, hope this clears your doubt, Salini. Oh, it has gone almost 2 hours. Okay, if there is no doubt, then should I close? I need your comments. Okay, thanks for attentive listening. Thanks for attentive listening, and this video I have started recording it. So once this record is available, I will try to upload it in the Google Class also, so that whoever has missed this lecture, they can get benefit from that. Okay, thank you all. Bye bye.